Hi everybody, welcome back. Today we're going to be talking about note 7.4, properties of logarithms. In this lesson, we're going to teach you how to take a single logarithm and expand it out, as well as taking an expanded logarithm and condensing it back into one logarithm. So let's jump in and let's get started. Okay, we're going to start off with some properties of logarithms. Now, we're going to use these properties to take a whole bunch of logs and condense them into one, but we're also going to use this property to take a logarithmic that's condensed and expand it out. So please know that these rules are kind of like if and only if statements in geometry. I know, I apologize, brought up some bad memories when I said geometry, but please remember that these rules can work, both ways, like a biconditional statement. So here we go. So the first rule we're going to talk about is the product rule. So if we have the log base b of m times n, when we expand that, that's going to expand into log base b of m plus log base b of n. Now, keep in mind, if you are taking the expanded form and condensing it back, so if you have the right side, here's the key thing though, when you're condensing logarithms, they have to have the same base. So if you have a log base 3 and a log base 2, you cannot condense those into one logarithm. Okay, so if I have log base b of m plus log base b of n, you can then condense those back into log base b of m times n. So if the arguments, that m times n, if that's being multiplied to expand it out, you expand it with addition. If it's an expanded form and you're going back to condensed form, you condense it back into a multiplication of those arguments. Now, this is just to show you that the rule holds true also if it's a natural log. So you're going to see that I put both the regular log and the natural log. These rules work for both of them. So that's the product rule. The quotient rule. The quotient rule says if I have log base b of m over n, then I can expand that with subtraction. So that becomes log base b of m minus log base b of n. Now, again, if you're starting with the expanded form and it's subtraction and you want to condense it, you always condense it with the first argument being divided by the second argument. And again, just showing you this property holds true for natural logs. Let's talk about the power property. So the power property says that if I have log base b of m to the piece power, then we can take that exponent and we can bring it down and put it right in front of the log. So I can take that exponent and turn it into a multiplication of exponent times that log. Okay? Conversely, if I have a p times log base b of m, I can take that p-value and I can send it up and make it an exponent of the argument. And again, just showing you that these rules hold true for the natural logs as well. Now, I know you're probably thinking, oh my gosh, this is theory. What is she talking about? So let's look at some examples. Okay, let's look at how we actually apply those properties now. Now this one says to simplify, to write each expression as a single logarithm. So if you're referring back to that chart we just did, we're going from the expanded form back to the condensed form. So we're going to take it and condense it into a single logarithm. So I have log base 7 of 5 plus log base 7 of x. So the first thing you want to check is, are my bases the same? Well, my bases are both 7. So yes, they are the same, and that means I can condense it into one logarithm. So this is addition, okay? This is addition. So to combine addition, we change it to one log where we multiply the arguments. So I end up with log base 7 of 5x, so 5 times x. Not too bad, right? Okay, let's look at our next example. Our next example says we have the natural log of 18 minus the natural log of 6. Well, again, check and make sure the bases are the same. Well, the base on a natural log is an e. The base is e. So yeah, natural log, they both have the same base. Okay, so now this is subtraction. So if I'm referring back to that chart where I have ln of m minus ln of n, remember to go back the other way. We're going to combine that using division. So I'm going to say, okay, well, that's the natural log of 18 over 6. Now, here's one thing you always need to be cognizant of, and you need to make sure you do. When you're changing it to division, the first argument is on top, and then whatever comes after the minus sign, that second argument, that goes on the denominator. Okay, so now we have a natural log of 18 over 6. Okay, if you can simplify it, please do. Do not leave that as 18 over 6. 18 divided by 6, y'all, is 3. So I'm going to simplify that further and say the natural log of 3. Okay, last example. This one is 3 log base 2 of x. Now, really, that's not how we read it. So let's talk about how we really read it. We see that as 3 times log base 2 of x. 3 times log base 2 of x. So this one isn't multiple logs, but it's a log with a leading coefficient, I guess, if you will. It's being multiplied by a factor. So since that 3 is out there in front of the log, that's going to be where it became p times the log. So we're going to take that coefficient and we're going to send it back up to be an exponent. So it looks like that. Log base 2 of x cubed. Now, I know what most of you are going to ask. So like, does it matter if I put the 3 inside the parentheses or outside the parentheses? And the answer is no, it does not. So you can write this as log base 2, open parentheses, x cubed, close parentheses, or you can write it as log base 2, open parentheses, x, close parentheses, exponent of 3. Both are mathematically legal. Now, the one thing I want to point out here is note we are simplifying. We are simplifying. We are not solving for x. We're not evaluating these. We are simply simplifying. So if it says to condense or expand, that's simplifying. If it says to evaluate, that's when you're going to take it that step further and solve that logarithm. So we'll look at one of those at the very end of our lesson. Okay, so here we're still rewriting each expression as a single logarithm. It's just now we have more than 2 logarithms in each expression. Now, the first thing you always look for is, do any of my logs have a leading coefficient? And right here I see that I've got a 2, and right here I see that I've got a 3. So the first thing I'm going to do is take that 2 and that 3 and then change them to be exponents. So that becomes the natural log of 3 plus the natural log of x squared plus the natural log of y cubed. Now, these are all addition. So what we're going to do is, remember to condense addition. We're going to condense that by multiplying the arguments. So we're going to multiply all those arguments together. So that becomes the natural log of 3x squared y cubed. Pretty easy, right? Let's look at our next one. Okay, same thing. We are going to look for, do any of them have leading coefficients? And this log does. So what we're going to do is we're going to send that 2 to be an exponent for x. Now, I know, especially if you're in my class, I have drilled it into your head that if you have a minus, always change it to plus a negative. Well, this is a little exception to the rule. Do not change that to plus a negative 2. Just leave it as minus, because then we can condense that with division. Okay, so the first thing I'm going to do is change that to be an x squared. Cool. Now I see that right here I have 2 that are being added. I have 2 that are being added. I apologize, that's a bad line. Let's try that again. Okay, so I have 2 logs that are being added. Okay, so to condense addition, we change that to a multiplication of the arguments. So I get log of x squared minus log of x squared. I know you're like, ooh, yeah, that's 0. I mean, if we were evaluating, yes, it would be. However, go back and read these instructions. It says write it as a single logarithm. So if we say that's 0, it's no longer a logarithm because you don't have a log in there, okay? So we're going to keep using our condensing rules. To condense subtraction, we change it to division. And x squared over x squared is 1. So our answer is log of 1. Now, again, we've talked about which means 10 to the 0th equals 1. So the simplified or evaluated answer is 0. But again, we were asked to write it as a single log. That's why we've got to keep the log in there. Okay, so now we're going the other way. We're going to go from the condensed version to the expanded version. So looking at our first example, I see that we have the natural log of 3a. Well, I see that I have 2 things in my argument that are being multiplied. So I'm going to stretch that out into the natural log of the first piece of that argument plus the natural log of the second piece. So it becomes natural log of 3 plus natural log of a. Now if we look at the next example, I have log base 3 of x divided by 5. Well, going back to my chart, to expand out division, I change it to subtraction. So that becomes log base 3 of x minus log base 3 of 5. Last example. The natural log of x to the 7th. So while I don't have multiple things that are being multiplied, that's an exponent. That's 7. So we're going to take that 7, that exponent, off of the argument, and we're going to send it down so that it sits in front of the ln. Now, there are 2 ways to write this depending on your preference. You can say 7 dot, the multiplication dot, ln x, or you can just say 7 ln x, okay? So, because that 7 with no sign in between the 7 and the natural log, that's an understood multiplication. So you don't have to put the multiplication symbol there. And again, please note, we are simplifying. We are not solving for x. We're strictly simplifying. No evaluation. Okay, so now we're going to expand. So we're still expanding, but this time we have multiple elements in our argument. So just more than 2. You know, in this case, we've got 3. So when you are expanding out a condensed logarithm, you kind of do things in kind of a different order. When you're expanding, the first thing you want to take care of is expanding out any division. So you've got to expand out the division first. So that becomes log base 6 of 4x minus log base 6 of y. Okay, now at this point, I don't have any exponents that I can bring down. However, I do have an argument that has two elements that are being multiplied. So I can expand out that multiplication to be log base 6 of 4 plus log base 6 of x minus log base 6 of y. And that is as expanded out as it can be. Let's look at our next example. The natural log of 4 divided by x squared. Remember, the first thing you want to take care of is get rid of that division. So we change that to be natural log of 4 minus natural log of x squared. Now we're still not as expanded as we can be because one of our arguments has an exponent. So I'm going to take that 2 and I'm going to send it down to be in front of the natural log of x. So that becomes the natural log of 4 minus 2 times the natural log of x. Again, still simplifying, not evaluating. Now, let's use those properties that we've just talked about to help us evaluate some expressions. The trick to evaluating an expression that has multiple logs is you have to condense it into a single log, set the single log equal to x or variable of your choice, and then convert that to an exponential to find the value of x. So let's take a look at what I'm talking about. Our first example is log base 2 of 4 minus log base 2 of 16. So I don't see any coefficients that need to become exponents of the argument, so we're good there, but I do see that I am subtracting 2 logs. So the way we combine a subtraction is by dividing the arguments. So that's going to become log base 2 of 4 over 16. Now, you'll notice that I already set it equal to x, so that way, when it's condensed and simplified, I can then just change it to an exponential. But before I do that, I notice that 4 over 16 will reduce to 1/4. So, now that I've condensed this into a single log, everything's as simplified as possible. I'm now going to convert this to an exponential. So this becomes 2 to the x power equals 1/4. Now, I know that 4 is a power of 2. It's 2 squared. But that 2 is in the denominator. So to bring that back up to the top, I have to make the exponent negative. So I'm taking that 2 squared that's in the bottom and I'm going to bring it back up to the top. So instead of 2 squared, it's going to be 2 to the negative 2. Now that my bases are equal, I can set the exponents equal. So therefore, x equals negative 2. Now, let's look at our next example. So we have log base 3 of 9 plus 2 times log base 3 of 3. Well, that coefficient of 2 needs to become an exponent of 3 first. So I change that to be log base 3 of 9 plus log base 3 of 3 squared, and of course I set it equal to x. Now 3 squared is 9, so I now have x equals log base 3 of 9 plus log base 3 of 9. Now I know what you're probably thinking, ooh, that's 2 times log base 3 of 9. But can't I just use the addition rule and multiply the arguments? You're going to come out with the same answer. So I get x equals log base 3 of 9 times 9. Now 9 times 9 is 81. Excellent. We have got that simplified as far as it can. So now we're going to change it to an exponential and see if we can find out what x is. So that becomes 3 to the x power equals 81. Now 81 is 3 to the 4th power. So 3 to the x power equals 3 to the 4th power. Therefore, x equals 4. All right, remember in an earlier lesson when we wanted to solve 2 to the zth power equals 6, and we were unable to because there was no power of 2 that was an integer that equaled 6? Well, today we're going to be able to solve that and find out what the power of z is. And to solve that, we're going to use something called the change of base. Now, what the change of base does is it takes any log that is not base 10 and converts it into a base 10 logarithm that we can then in turn type into our calculator. So let's look at the change of base formula. So if we have log base b of x, the change of base formula says we are going to take the log of x and divide it by the log of b. So again, what you're going to be doing is you're going to be taking log of the argument divided by log of the base. And when we do this, these logs are now base 10 logs. Let's look at an example. So if we have log base 2 of 7, using the change of base, we are going to do log of 7 divided by log of 2. Now, when you type this into your calculator, trust me on this, take it one step at a time. So you will do log 7, enter, divided by log 2, enter. So let me say that again. Log 7, enter, divided by log 2, enter. And then once you hit enter that last time, it tells us that log base 2 of 7 is approximately 2.807. Now, let's see how this applies to our 2 to the zth problem. So we know we can't solve 2 to the zth equals 6 right now. So we have to convert it to a logarithm. So that's going to be log base 2 of 6 equals z. Now, because this is not a base 10 logarithm, I cannot enter it into my calculator yet. I have to convert it to a base 10 using change of base. So I'm going to do log of 6 divided by log of 2. Again, please make sure you enter this as two separate steps. So log 6, enter, divided by log 2, enter. And when you type that into your calculator, you get that z is approximately 2.585. Now this is not equivalent to log 3, so you cannot say, oh, it's log over log, therefore it's log 3. No, that's not how it works, because you're taking the value of log of 6 and you're dividing it by the log of 2. So that's why we end up with 2.585. All right, so that's the end of our lesson on properties of logs. You may now go start on your worksheet 7.4. And if you have any questions, please ask your teacher. If you need any help, that's what we're here for. Please remember to wash those hands, social distance, wear a mask, stay 6 feet apart, and make great decisions. And we'll see you back next time. Have a great one, guys. Bye-bye.